any questions before we start? Either you want to have something Okay, we got a lot of material, so I'm going to go ahead and get started. And I'll review briefly what we talked about last time. So last time we were talking about the energy levels of a particle in a box. And we were looking at solutions to the Schrödinger equation. So we had the solutions to the Schrödinger equation, which was minus h bar squared over 2m times the second derivative of phi with respect to x. Let's see, equals e times the energy e times the function phi of x, right? And we worked through the solutions, and what we said was that the usefulness of this equation is that it tells us what are the allowed energy levels that a particle can have, and it allows us to solve for the probability function, or what we call the probability amplitude, phi. Because this is important because we know that the probability of finding the particle in the box, the probability density, is given by the magnitude of phi x squared, which, if it's complex, is going to be equal to the complex conjugate of phi times phi, right? And if it's real, then you just square the function, right? And we talked about that, and I gave you a handout on some complex variable function formulas last time. If you did not get them, I have extra copies up here from last time. So you review a little bit about what a complex variable is. Okay. So the result that we got was that if we require that a particle be constrained to bounce around in this box with some definite energies, then there are only discrete energies that are allowed. And the energy levels that are allowed, which we'll call this one E1, and then we'll call this one E2, and we'll call this one E, etc., right? And go all the way up. Now, because the walls of the box are infinitely high, which means that the potential is infinite for x less than or equal to 0, and also for x greater than or equal to L, then the wave functions must vanish at the edge of the box. So in other words, if I'm to draw what the solutions phi of x are, so phi of x, so phi of x is the wave function, then we had solutions that look like the half integer of a wavelength. We had solutions that looked like one integer wavelength, and then we had one that was sort of like this. Right? And I'm trying to see if I've drawn that right. 1, 2, 3, yeah, one more half right here. Coming down. So these would be the first three energy levels of and the wave functions for the particle in a box, and they were discretized. In other words, they were only allowed in discrete numbers. So this was probably the first example of a quantum solution to a particle that is constrained, right? So we agreed that these are bound states. The particle cannot escape the walls. This is what we end up with. Now we also solve for the energy levels. The energy levels are E sub n was equal to n squared times h bar c quantity squared divided by 2 me quantity c squared divided by L squared, and let's see if I left something out. Factor 2. No, 2. This was 2 times. There's my eraser. I believe I'm missing. This is factor of 8. Right? This is factor of 8. Right? And this particular, if we were to solve this or evaluate this for electrons, then I could simplify this and calculate all the constants, and this was 0.376 times n squared over L squared, and this has units of EV nanometers squared. Right? So this gives us a much simpler way to calculate the energy levels, and of course I can have n equals 1, 2, 3 all the way up. Right? So there's an infinite number of values of n. The walls are infinitely high, so I can always stack more energy levels on top. And by the way, as this is a potential energy diagram, this is the value of U equals 0 is down here, right? And that's where we have it right here. And consequently, as we've said before, the difference between the energy and the potential function is the kinetic energy. So in this case, these also represent kinetic energy, right? EK1. And then up to here will be EK2. Right? And up to here is EK3. So in other words, in this particular case, these are equal to 1/2 mv squared. That's what we're saying. Right? That this is the way of looking at this, and or we could write that this is equal to the momentum squared, p squared over 2m. Okay, that's sort of where we left off. Now, there's a couple things we can think about here. First of all, there's a definition that you should be aware of, and that is that this is called, this particular, I'll write out what phi is here in a minute. This particular, get the right color here. This is good. This particular one is called the ground state energy. So this is the ground state or energy, or what's called the 0 point energy. 0 point energy. So this is the least energy that a particle in a box can have. In other words, you might think that if I were to actually put a particle in a box, I could give it any velocity I want, and it would remain in that box at that velocity. And that is true classically. Classically, if I were to use, for example, a pinball or a ping pong ball or a BB or a small object or a puck on the ice, as Deborah Katz talks about, then the particle just will slosh back and forth across here, and it can have any energy at once. The interesting thing about a quantum system is that this is the minimum energy. It is not possible for the particle to have any kinetic energy less than this amount. Now you might find that kind of odd, because you can say, well, I can make a box and I can throw a ping pong in there and I can make that velocity go as slow as I want. There's no constraint at all. But that's because you're not able to measure really, really small velocities. In particular, if I were to say the ground state energy corresponds to a velocity which is 10 to the minus 31 centimeters per second, I'm going to say you will not be able to measure that. Okay? You'll never be able to measure something that small. But in actual fact, there is a minimum energy for that ice puck on the ice, or the ping pong ball sloshing back and forth to have. It just happens to be so small that we can't measure it. Okay? No way to measure it. So for all practical purposes, it's the ball's at rest. Right? Okay, so we get into kind of a new phenomena here when we talk about really, really small particles and very, very short distances. Because you notice these are in units of electron volts, which is, electron volts is a unit which has units of 10 to the minus 19 joules, and a nanometer, which is of units 10 to the minus 9 meters. So these are energies and distances that we normally don't deal with. Right? So there's a quantum behavior at the microscopic level. And because of these very, very small energies and distances, it turns out that there are observable effects where we can actually prove or show that certain atomic systems behave this way, even though in our ordinary world we would say that would never be possible. Okay? You might also suspect that if I were to, but we'll come back to that later. Now, one other thing that, and there will be some problems on this as well, but one other thing that the way we actually confirm a theory is that we don't actually have measurements of these wave functions. And we don't usually have measurements directly of these energies. But what we do have measurements of are transitions of particles from one energy to another. So in other words, supposing I have a particle sitting at this energy level right here, right? And we'll come back to what that means, but basically it has a fixed energy, it has a fixed momentum, it's got a fixed speed, and it's just moving back and forth. Right? I now can hit that object, or that microscopic object, with a photon, and if I hit it at the right frequency, then I can pump this electron up to a higher energy state. Right? At some later time, then the photon, the electron or the particle here is going to come back down. And when it comes back down, it's going to emit a photon. Right? So, and it's going to have energy E equal to h times the frequency. Right? That's the energy of the photon. So there are, and we'll see this a lot when we look at the hydrogen atom, for example, that we can actually measure these frequencies that occur once an atom has been excited, and then, or an electron has been excited, and then it's allowed to de-excite, and it gives off photons. And by measuring these energies, I can confirm that E2 minus E1 is what I measured. E3 minus E1 is what I measured for this energy, or E3 minus E2. If this one comes back down to another quantum level right here, it emits a photon of energy h times the frequency. This would be F1, for example, and this would be EF2, it's at HF2, for example. So that's how we actually confirm that quantum systems are working the way we think we are. We don't actually, I can't find a way to measure these probability functions, but I can excite the system by perturbing it and pumping electrons into a higher energy state and wait till they decay back down. And I can observe what the frequency or the wavelength of that radiation is. Once I know that frequency, I can confirm whether my model is correct. Does it have the energies that are consistent with this equation? Right? So that's how we actually test that quantum systems work. We can't measure these quantities directly. Now, speaking of these wave functions, so I said I was going to write down the wave function. The wave function for these different particles. So the nth energy level wave function is equal to the square root of 2 divided by L times the sine of Kn times x, where Nk is the wave number and Kn is equal to n pi divided by lambda, and lambda will be, we'll say lambda sub n for the nth wave, and this will be related to the energy by n pi over, this will be, I'm trying to think of the easiest way to get to this. N pi over L, and this was equal to the square root of 2 pi E sub n, the nth energy level, divided by h bar squared. And that happens to be this value. Well, this happens to be, I have to rewrite the equation again, sorry. Rewriting the Schrödinger equation, this is the coefficient in front of the second term, which is d squared phi dx squared, plus 2me divided by h bar squared times phi of x is equal to 0, right? And this is, of course, what we said was equal to k squared, or in this case, k sub n squared. So we quantize the energies according to this formula. This formula allows us to actually state exactly what the energies are going to be. I think there was one more equation I probably left out here. This is, one second. The allowed values of lambda n, which is the wavelength of the particle in the box, is given by is given by 2L over n. Right? So in other words, for the ground energy state, I can have, this shows you that lambda is equal to 2 times L. For the energy E2 state, lambda is equal to L. For the energy of the third state, for E3, I can write down that lambda is equal to 2/3 of L. And in general, I can then get that lambda for the nth energy level is equal to 2L divided by n. Right? So this is basically found from the boundary conditions. Notice that the particle cannot go beyond the wall of the box. The probability has to go to 0 at this end of the box and at this end of the box. And furthermore, if I want to calculate a probability, then I have to square the wave function. Right? So I have to use this formula right here, that the probability is the square of the amplitude. So I use this formula. If I use this formula right here, then what I can do or find is that the probability distributions for the particle in the box are given by, for E1, so here's E1. I square this function. Okay, that doesn't change very much. It just becomes the square, right? So it becomes like this. If I go up to E2, I square the sine function. It becomes like this. This is a sine squared function. If I square the wave function for the third energy state, which I'll call E3, then I'm going to get a probability distribution, which is the square of this. So it's going to look like this, like this, like this. Okay? So these represent the probability of finding the particle in the box. Right? Now, Deborah Katz in the textbooks likes to point out that this is an unusual non-classical event, that if I was dealing with a hockey puck on a frictionless surface of ice, where the puck is just simply going back and forth, then I would expect, in particular, if I did the experiment 100 times, and I wanted to find out what was the probability of finding the particle at a given location, then what I would probably expect to find for any given energy, let's say E sub n, what I would expect to find is that the probability distribution is flat. It would probably be the same. It would be the same here as it is here as here. In other words, if the puck is just going back and forth, and I don't know when the puck was inserted in the box, and I make a measurement in arbitrary time t, it's just as likely to be found here as it is here, right? And that is the classical result. The quantum result is that depending on the energy of the particle, it can be found here and here, but with different probabilities. And notice that even though the particle seems in your mind is oscillating back and forth, it can never go through a point where the probability is equal to 0. Right? Here, here, here. Those are called the nodes. That's a difficult thing to comprehend. because you could say, well, if the particle is moving back and forth and it's got a fixed momentum, right, then clearly the only way it gets from here to here is to go through the middle. Right? But you're telling me it can never be at the middle. And the answer is yes, because it's not acting like a particle, it's acting like a wave. And there's no other better explanation, and you may not even like that explanation. But the point is that we're describing the probability of particle moving back and forth, but there are certain positions in which the particle can never be found. And that is a strange phenomenon. You know, I don't have an explanation why this is true. It is a quantum mechanical result. And it's something that you learn and you can only understand by thinking of the particle as a wave. Right? In the book, they talk about analyzing the nodes of a stringed instrument. And in the nodes of a stringed instrument, if you fix a string at 2 points, then the vibration of the string can go up and down, and then back up and down. And the oscillation of the string goes from here to here to here to here to here, back up again. And the time from here to here, or the frequency, is 1 over the time it takes, or how many oscillations that the string makes per second, right? That's what the frequency is. This is the frequency of a string. But there are points here and here where at the end of the string that the string cannot move and the displacement is 0. If I have a higher harmonic of this, and by the way, this can be a guitar string, it can be a piano string, it can be a violin string. If I have a higher harmonic of this, then I might have one in which I can have one in which it does this. And then it does this, and then it does this, and then it does this, and then it does this. And then it starts to go back and does this again, and then the amplitude decreases. But there's a point in between here where the string has 0 displacement. Right? And this is called a harmonic of the fundamental frequency. And this is analogous to the picture that we've drawn here, where there are certain points where the probability is 0, and it's acting very much like a wave. Right? There's no better explanation. I mean, I can talk I can talk on and on and on, but I don't think it will get any clearer. But you can ask a question. Let me see. Somewhere in the rest of the notes. While you're thinking of it. Okay, question. Any questions? Yeah. Quantum systems work differently. I guess that's the best thing we can say at this point. What's the other thing to say? Okay, so there's one other important point that is worth looking at here regarding, again, we're going back and forth between the picture and the wave picture of what's going on here. Let's look at another level of detail, and that is that we said that the energy is fixed, quantized, the momentum is quantized, and therefore the velocity is quantized. V is fixed, right? So if this is the energy of the particle in the box, then that's momentum, of course, is fixed, and obviously, therefore, yeah, right? I mean, this makes sense, right? The velocity cannot be fixed. But, however, we do know that if it is a particle moving back and forth, that once it's going this way with velocity v, or momentum, we'll call it p1, right? Once it hits the wall, it comes back with a momentum in the other direction, p2. Right? So how did the particle change from going from momentum p1 to p2 if the momentum is never allowed to change? If the energy is fixed, then the momentum is fixed. But if the particle is moving back and forth, it's got to reverse directions when it gets to the wall. So that means that at some point, the momentum has to go to 0, right? Because it slows down and then speeds up again. Okay? So how can that be true if the energy is quantized? Well, the answer is it lies in what's called the uncertainty principle. Anybody familiar? Ever heard that word before? Okay, so now we're going to talk about Heisenberg uncertainty principle. So the uncertainty principle says that, and we'll give another example of this as well. But the uncertainty principle says that if I have the location of a particle has an uncertainty of value delta x. In our case, delta x is equal to m, right? This represents what we call the uncertainty of the particle. In other words, if we were to calculate the uncertainty of position, if we were to calculate the average position of the particle in the box, it would always be at the same value, L over 2. Right? So delta x actually is going to be equal to L over 2. Right? In other words, what it means is that all I can tell you when the particle is located between here and here is that the best description of the position of the particle I can give you is that it is located at a coordinate x equal to L over 2 plus or minus L over 2. Right? That's the best I can tell you about the particle. I don't have any other way to make a measurement once I know the particle is confined between 0 and L. Right? So this represents L over 2 is the uncertainty of where it is in the box. Right? The Heisenberg uncertainty principle then says that there's a corresponding uncertainty in momentum, so delta P is equal to the uncertainty in the momentum of the particle, of momentum. Okay. And the product of these two, delta x times delta p, can never be less than, must always be greater than h divided by 2 pi. Actually, h divided by 4 pi, I believe, is the correct answer. But, okay. This means that there is always a minimum uncertainty. Okay. There's a homework problem. Some of you actually went ahead and started doing this. I noticed on the homework last night. That's okay. I wanted a chance to try to explain a little bit, but that's fine. You learn by doing problems as well as thinking about the theory. But this is the statement of the Heisenberg uncertainty principle. Right? Now, this is exactly what it means. So let's see, how can we apply it to this particular case? We know what the uncertainty in the position. If there's a particle in the box and it's somewhere between 0 and L, we know the uncertainty is L over 2. Right? What is its uncertainty in momentum? Well, we just said that in going in the forward direction, P1, it's going to have momentum equal to 2m times the square root of E1. Actually, this is probably a wrong bad notation. Let me see if I call this P1 and P2, but they're actually, for the, trying to think of a better way of doing this. Let me see if I can do this. E1. And by the way, E1 is given by the energy equation, which says that this is equal to h bar c squared. I'm doing this for n equals 1 divided by. Well, why don't I just do it for electron? That makes it a little bit easier, right? Let's do it for an electron. N equals 1. We say then that E1 is equal to 0.376 divided by L squared. Now, P2 is the momentum when it changes direction. It's not the second energy, but it's what is the momentum in this direction? It's opposite P1, right? So this is equal to minus P1 because it's just changed direction. So that's equal to the square root of 2m E1. All right? Oh, with a negative sign. I'm sorry, negative. Everyone got that? Minus square root of 2m E1. Minus. So when it changes momentum, what's when it changes momentum, the delta P is equal to the square root of 2mE1 minus the square root of 2mE1, which, or minus the negative, I'm sorry, minus the negative of, let me try to make this bigger so you can see it better, minus the negative of the square root of 2mE1, right, which is equal to 2 times the square root of 2mE1. Right? So this is the change of momentum when it turns around, or what I'm going to call the uncertainty in the momentum. In other words, I only know that this particle has a certain momentum which I have ascribed to it, plus or minus this amount of uncertainty. And if I now use the energy formula, so I can now let's see if I did this right. Show that if E1 is equal to, what is the value of E1? Now I have to go back to the H bar and the C. So let me do this one more time. H bar squared, and I'm going to do this divided by 8. H bar C squared times 8 times MEC squared times L squared. Okay, once I do the substitution, this is equal to H over L. Okay, so the uncertainty principle then says that if I take this uncertainty in delta X and I multiply it by this uncertainty in delta P, that the product has to always be greater than or equal to this quantity. So I can now plug this in and see what I get. What I will find is then that if I take delta X times delta P, this is equal to L over 2, and delta P is equal to H over L, which is equal to H over 2. Okay. Now, that's not quite the same as this quantity, which is H over 4 pi, but I'm going to make another qualifier on this, and that is that when we define these quantities, we actually talk about the RMS error. So delta X RMS times the uncertainty in the momentum in its RMS. So is everyone familiar with the idea that if I have a system of measurements, a group of measurements of a quantity, I can calculate the average and I can calculate the standard deviation? Everyone familiar with that? I want to measure the length of this table, I do it 100 times, I get an average value and I get a standard deviation. Right? This is the standard deviation. Okay? Now the standard deviation is actually square root of 3 times smaller than this. So if I put in the standard deviation, then it actually gets smaller by, and I'm not going to prove that here, but I'm trying to get you closer to this result to show you what we were actually trying to achieve. And this one is the momentum in the forward direction minus the momentum in the backward direction, which is the complete change in momentum. But the RMS of that is 2 times the square root of 3 smaller also. So this becomes H over L times 2 times the square root of 3. And this is the delta P RMS, or delta P of the standard deviation. And this is the delta X, the uncertainty in the position, by its RMS position. And now I get that the product of these is equal to H divided by 4 times 3, which is approximately equal to H divided by 4 pi. Okay? So even though this number looks larger and is larger than what's stated in the uncertainty principle, it's because the uncertainty principle uses standard deviations, not maximum errors. Right? In other words, what I've calculated here with these values are maximum errors. These are maximum uncertainties. Okay? The RMS uncertainty is small. Right? You understand that? Look, if I make a measurement of length of this table, right? If I make the measurement of length of this table and it centers at, let's say it centers at 40 inches, but the endpoint here and here is, this is 40.1 inch, and this one here is at 39.9 inches, and this is the number of measurements on this axis, right? This is the number of measurements of the length of the table. Then what I get is that the sigma, the standard deviation, so this is the mean. So the average value of the length of the table, x bar, is equal to 40 inches, right? But the standard deviation, plus or minus, is going to be 0.1 divided by some number, which is of the order of 3. For example, and, or actually it's 2 times the square, something of that order, right? So, in other words, the RMS error, which is the way we quote errors, it means what is the region around 40 inches of which 2/3 of those error measurements occur, then that error is significantly smaller, and this is what we call the delta X RMS. Okay? So the reason why I had to go this explanation is because what I calculated here was maximum uncertainty in the position times the maximum uncertainty in the momentum. And that gives me a number which is smaller than the uncertainty principle, but that's because the uncertainty principle uses RMS instead of maximum errors. Right? It uses RMS uncertainty rather than maximum uncertainty. Right? Is this clear? I'm sorry to digress, but so this is one of the key statements of the Heisenberg uncertainty principle, and basically it's saying that another way of saying this is that momentum conservation can and will be violated by an amount delta p if it occurs, as long as it occurs as long as the delta p is less than h bar over 2 times delta x. Yeah, maybe that's probably not a better way of describing it. But the basic idea is that the uncertainty principle allows us to incorporate the idea that yes, the momentum is going to change from p1 to 0 and back up to p1 in the opposite direction, but it's allowed to do that up to the limits of the uncertainty principle. Right? So in other words, it's saying that momentum conservation can and will be violated by an amount delta p, as long as that it is within the bounds of this equation. Okay. Now, let me give you another example of the uncertainty principle, one I like much better, but I will stop here for questions. If you tend to go kind of fast here. So everyone understand there's a dilemma here. The particle is changing momentum when it bounces off the wall. It seems not to be allowed to change momentum, but I'm going to get it by with it because I have another rule that's called the uncertainty principle that says the momentum can in fact be uncertain by a certain amount and be allowed to violate momentum conservation as long as the product of delta p and delta x is of the order of h bar divided by 2. So it's a caveat to the Schroeder equation. Oh, by the way, and I don't actually mean by the way, but I mean the problem is saying to you, by the way, momentum does not have to be conserved in a quantum system, because there's another principle involved, which is called the uncertainty principle. Now, let me give you another example of why the uncertainty principle seems to be hold true. It certainly allows us to get out of this dilemma. And the dilemma is that the particle has to be moved back and forth. Now, it doesn't get us out of the dilemma of how does it get across the nodes, how does it get from here to here without going through regions where the probability is 0? That question I cannot answer for you. All right? The only thing I'm going to say about that is it's not acting like a particle, it acts like a wave. And yes, it can be here, here, and here with these probabilities, but it can't be at the nodes. All right, I think I've covered as much as I can on the infinite particle in a box. What I want to do for the remainder of the time we have is to look at what happens when the depth of the box is not infinite. So right now we looked at a case where the physical barrier of the well was infinite at the edges of the box, and the potential was 0, but there are infinite number of energy levels that are available. Right? And this is because of the fact that the well, or the height of the potential energy, goes up to infinity. Now, if I have a different case, which is the one we're going to look at next, which is the one where the potential well is finite. So in this case, we're going to say U is equal to U0. And this is the same on both sides of the well. And of course, U is equal to 0 in the middle, right, where the well is. And the length of the box is length L. Now it turns out that the wave functions and the energy levels are going to be somewhat different. Okay? So what we're going to do now is to try to solve, and I mean by try, literally try, we can't really do it analytically in class, is to look at what are solutions for the energy levels for a finite well. And also, what are the wave functions for a finite well? So the basic idea of how we're going to tackle this is that we are going to write down the Schrodinger equation. Let me erase all this first. Keep remembering putting these caps back on, or all my ink goes away. Okay, so the first way we're going to try to solve this problem is to write down what are the equations that we need to solve for the wave function in order to solve this particular problem. Right? Now, bear in mind, the classical analogy to this problem is the following. Let's suppose that I have a ball rolling down a hill, and the ball rolls up the hill, and I now have a certain amount of kinetic energy located, for example, at the bottom of the hill, right? So this ball can slosh up and down with some kinetic energy, and it will go back and forth, but unless it has enough kinetic energy, or total energy, it cannot make it up over here to the top of the hill. So up here, where the ball is located, or could be located, this one, if this distance, which we call mgh, which is the potential energy of the system, is greater than the maximum kinetic energy, which is the kinetic energy of the ball at the bottom of the hill as it's sloshing back and forth, then the ball cannot escape. The ball cannot escape, right? So it's like a trapped ball in a well, right? If that ball doesn't have enough kinetic energy, it's not going to get up and be able to get out of the well. It's going to turn out, we'll find out, that in quantum systems, it can make it up here, but it's going to fall back in a very short time. But it can at least violate energy conservation up to a small amount of that is allowed by the uncertainty principle, which we'll talk about. Okay, so the first step in doing this problem is let's look at the Schroeder equation in these two. Now, in the Schroeder equation, we're now in regions, so I'm going to call this region 1, and this is region 2, and this is region 3. Right? And in region 1 and 3, the Schroeder equation is going to look like minus h bar squared over 2m times the second derivative of phi with respect to x, 5x, right? This will be plus u0 times 5x is equal to e times 5x. And I want bound solutions. So bound solutions means that E, which is the kinetic energy, of course, in the box, E is less than U0. Right? So I have a bound condition when the energy of the ball, so this is the energy of the particle, the energy of the particle is less than the height of the potential barrier, which in a classical system we would say that was mgh, but that's the potential energy of a gravitational barrier. Okay, so in order to solve this, what we do is what we're going to do is we're going to write it in the following form. We'll bring this over to the other side of the equation. We'll multiply by minus 2m over h bar squared, and we'll get the d squared phi by dx squared is going to be equal, this is going to be equal to minus, and now I'm going to do e minus e, minus e, minus e, pen, eraser, minus u0 minus e divided by u0 minus e divided by h bar squared, and this gets multiplied by 2m and times 5x is equal to 0. Okay? And we've just said that u0 is greater than e. So this has the form of an equation, of a differential equation that we can write as d phi squared by dx squared minus, and we're going to call this quantity as the coefficient of phi, capital G squared. So this will be minus g squared times phi of x is equal to 0. Right? So this is the Schroeder equation. So this is the S equation in region 1 and region 3. Okay? This is the Schroeder equation. This is a second order differential equation. G is squared, of course, is positive, as we can see here. And now I have to come up with a solution. Okay? So in order to do that and to find a solution, well, there are various techniques we can use, but the easiest one to do is to write down a value that I think will work and then plug it in and see if in fact it does. And it turns out that there are actually two solutions to this equation that will work. One of them is going to be of the form, I'll explain the constants later, c e to the, let's put it this way. The two solutions are the form e to the plus gx and e to the minus gx. And the most general solution will be any linear combination of the two, which will be, in this case, c C e to the gx plus d times e to the minus gx. Okay? So basically what you can do is to put either one of these functions into this equation and show that this function or this function will satisfy this equation. Right? So you substitute in the value of phi, either e to the plus gx or e to the minus gx, and show that in fact they work. Now because these two functions are independent of each other. The most general solution is found by taking the linear combination. So remember that we said that a second order differential equation will have two independent functions that are not linearly dependent. Two independent functions that, that both solve this equation. And the most general solution will be one that is a linear combination. And the linear combination is any constant C and D given by this. But now we determine C and D because of boundary conditions. So we can find C and D from boundary conditions. Okay? Find C and D from boundary conditions. Okay, so here's one idea we have. Since these solutions will work in regions, in regions 1 and 3, here's one boundary condition that I think we can all agree on, and that is that if there's a probability of being the particle which we know is trapped in the well, and there is now a probability that it can exceed the boundary of the well by a certain amount, then the probability must go to 0 as x goes to infinity. So p of x must go to 0 as x goes to infinity. In other words, the particle is not free to move along the x-axis, so the probability must in fact diminish or decrease as we move away from the boundary of the well. If it's going to spend any time outside the boundary, it has to do in a way in which it becomes less likely, not more likely, to be found out in this region. Okay, so what we're going to do then is to say that in this region right here, the solution, which I'll write as phi 3 of x, is going to be equal to e to the minus, it's going to be equal to d times e to the minus g times x, right? And over here in region 1, I'm going to have a solution which also where the wave function has to advantage at minus infinity. So I'm going to get that phi 1 of x is going to be equal to c times e to the plus gx. Right? So as x goes to minus infinity, e to the gx goes to 0. So this will also have to satisfy the condition that the probability, which is the function squared of x, goes to 0 as x goes to negative infinity. Okay? So I have now eliminated one of the constants in each side of the well, namely that this is the equation of the solution of the wave equation in this region, and this is the solution of the wave equation in the region on the other side of the well. All right? So I now have two solutions involved here. Okay, now the question is, what is the solution in the middle? So now I need to know what is the solution phi 2 of x. Okay. What is that solution? In the region phi 2, right? In phi 2, we know that can someone shut the doors out there? I'm sorry, I feel like I'm yelling and I need the last 4 minutes to right? That u0 is equal to 0, right? So now what this says is I'm basically going to get the same solution as I had before with the particle in the box, which is a sine of kx plus b times cosine of kx. And thank you for showing that. Thank you. So remember we had this solution before, but we threw away this term because it turned out that at x equals 0, the wave function had to go to 0, but the only way that could happen is if b was equal to 0. And now we are no longer requiring, so now the wave function does not have to vanish So we know that the wave function psi 2 of x does not vanish at x equals 0 or x equal to L, right? So now we don't need to throw away this term, and we're going to keep this term as part of the solution to the wave equation in this region too. So that means that we now have 3 solutions in 3 separate regions. So we have psi 1 of x is equal to c times, I'm just repeating what we have over here so I can put them all together, plus c e to the plus gx, and psi 3 of x is equal to d times e to the minus g times x. Right? So I now have the solutions in the middle and on both edges of the box. And the difference is that in spite of classical theory, which says that if the kinetic energy is less than the height of the potential, the ball cannot get out of the well, we find that sometimes the ball does get out of the well, but it can only remain there for a certain length of time before it has to get back in here. Right? In other words, energy conservation can be violated up to a certain amount as long as it happens over a time interval t which is small enough. And that's another aspect of the uncertainty principle. So the second statement of the uncertainty principle is that the uncertainty in the energy times the time over which the energy conservation can be violated is greater than or equal to h bar divided by 2. Okay? So this is the second uncertainty principle. And the first uncertainty principle, which is what we had before, said that delta x times delta p, can't draw this right, is that delta x times delta p is greater than or equal to h bar over 2. Okay? So we're now going to be looking at cases where both the spatial and momentum uncertainty holds, but also where what's called the energy and the time uncertainty principle holds. And this uncertainty principle is a way of, you might say, of making it palatable or legitimate that particles can be found in regions where they are classically forbidden. In particular, when the kinetic energy of the particle in the well is less than the height of the barrier. Classically, the particle cannot get out. Quantum mechanically, it can get out, but it can only be out for a short time, and the time in which it can be out is of the order of h bar divided by 2 times delta E. So the amount by which energy conservation can be violated, so this is violation of energy conservation, can occur if it occurs over a time such that that time does not exceed h bar divided by 2 times delta E. Right? And similarly, momentum conservation can be violated by an amount delta P as long as that it occurs over a distance delta x, which is of the order of h bar divided by 2 times delta P. So momentum conservation can be violated by this amount. Right? And that amount is delta P, and the amount delta P is given by this expression right here. Okay, we'll continue next time. I think you have enough information to at least get your chapter 41 homework, part 1, finished and solved for. So I think we've got enough to make hopefully substantial progress. Yeah, do you have a question?
I just want to make sure, is that the third equation down from your last gravity level, is that supposed to be d squared
Where are you?
Center of the board,
Yes.
bottom equation, to your right. Yep, that one.
This one,
Yeah, is that supposed to be d squared phi?
that's a G.
No, on the left.
Left.
Is it supposed to be the second derivative of it, or are you squaring phi?
This is the second derivative.
Right,
That's the second derivative.
right.
Should be
You
decent.
you had, you
The
had,
notation was just.
yeah, the notation is written different.
What? Say it.
The notation is off from a second derivative, I just wanted to make sure that it was the second.
Yeah, but which one is it? I want to make sure. that-
You were on the right one.
Yeah, you would be.
Oh, I'm sorry. Yes, thank you. Yes, yes. Second derivative, yes. Yeah, thank you.
I
Yes.
just.
Good thing you brought it up. Yes, thank you.